everyone, welcome into lecture number 8 of differential equations. This lecture is on first order difference equations. So let's talk about what a first order difference equation is. It's pretty much exactly what it sounds like in the following setting. So sometimes in modeling physical phenomena, it is easier to work with discrete data than with actual continuous data. So let's write it this way, but when working with discrete data, we can make the following kind of a model. So discrete data, we can model population y at time n by a sequence instead of a function, right? But so at time we'll say n here, where n is an integer, 0, 1, 2, 3, etc., by the following formula. So something like the following. So y sub 0 will be alpha. This is our initial population. And it doesn't have to be population, but I'm just using population as an example here, like a motivating example. But initial population. And then future times y equals n, y sub n plus 1. So now the main deal here is that your n is only allowed to be an integer. So a whole number, right? A whole number. Then y sub n plus 1 is going to be given by some function of n and the previous value, y sub n. All right, and so again, this is for n equal to 0, 1, 2, etc. And the function f then determines, it's like the right-hand side of a differential equation, right? But because the data is discrete, this is called a first-order difference equation with this initial value in this case. All right, so this scenario, this is a first order difference equation with an initial value, or with initial data. All right, so it is also possible, and we'll start by studying this kind, but just like a differential equation, it's possible that our difference equations can be autonomous. And so autonomous would mean that the function on the right-hand side does not depend on n. All right, so like differential equations, then we get the following. A difference equation. The initials are DE for both, so it's helpful there, right? But a difference equation is autonomous if f is equal to just a function of the previous value. And in other words, if it doesn't depend on n, right? If it doesn't depend on just n. It depends on y sub n, but not on n. So that's the difference, right? There's no n here. Okay, so let's look at some examples, and then we'll see how these work. So our job is going to be to try to find a way to write down the solution for any n, any time n. All right, so here for this one, this will be our first example. Let's suppose that we have a real number rho. So suppose rho is a real number and that it is fixed. All right, and consider the following difference equation. So this difference equation is going to be like as simple as we can get. This is like our linear first order difference equation. So y sub n plus 1 is just going to be equal to rho times y sub n. Well, this one is very simple to solve, right? Because if we know, so if our y sub 0 is equal to alpha, then we can easily compute the value of y sub n just by plugging in, right? So you can verify this, but y sub n, what's it going to do? Well, every time that you multiply, that you increase n, it's going to multiply by rho, right? So it's going to end up being rho to the power n times the initial value, alpha. So times the initial condition, alpha. All right. Now, this equation, so this is the general solution, right, given an initial value. So this solution works given an initial value, alpha, and this alpha could be any real number, right? So any real number. If you're thinking of it as an actual population, it's probably a whole number, but that's fine. So that's our alpha. You could, though, consider this to be a function, these solutions to be general solutions, right, in terms of alpha as a function of alpha, if alpha is allowed to vary. So for different initial values. And we can talk then about the equilibrium solution. So this difference equation has an equilibrium solution. What's it going to be? Think about it while I write here. Remember, equilibrium solution means that from one moment to the next, nothing is changing, right? So for our differential equations, that would mean that the derivative would be equal to 0. In this case, it means that y sub n is for this particular example, it means that y sub n is equal to 0 for all n, right? Because if you think about it, if you're multiplying by rho, right, then rho, that's going to change if rho is non-zero. So if rho is not 0, then that's going to change the value of your population for all values of the population except for 0, right? So multiplying 0 by rho is still going to give you 0, no matter how many times you multiply by rho. So that's why that's the equilibrium solution. And we can also think about what happens to this solution, this one right here, right, as time goes on. All right. So, and as time increases. Time here is denoted by n. It's discrete values of time, but we can still think of it as time. Then we get the limit as n approaches infinity. Y sub n. There's 3 cases. All right. So on one hand, this is going to equal 0 if the absolute value of rho is less than 1. So if this rho is smaller than 1, then every time you multiply by alpha, it's going to make the value of the population smaller, right? So the population size will decrease until after a long time, there's no population left, right? It's going to equal just the initial, which we called alpha, right? So it's going to equal the initial population value if rho is equal to 1. Okay, so if rho equals 1, then nothing changes, right? So you multiply by 1 every time, the population doesn't change, and it just stays constant at alpha. So that's another example. That's kind of an equilibrium, but that actually every solution is an equilibrium. So that's not exactly the same, right? So when rho is equal to 1, that's a totally different kind of differential equation, actually. But then the real thing that happens here is that when rho is larger than 1, if the magnitude of rho is larger than 1, then the population grows unchecked, right? So the population, the limit here, the limiting population does not exist, right? Otherwise, for all other values of rho. So these are the different possibilities of how these solutions can behave, okay? So what we would like to do now then is add some complexity to this model. So right now this model just says, all right, there's a growth rate, call it rho. From year to year, maybe you measure your time in years, maybe you measure your n in months. You can measure whatever you want. But from year to year, you multiply by rho times the current population, right? And that gives you your new population. So that's the simplest kind of model. Now the second thing that we can do to modify this model is that we can consider immigration. So let's consider immigration now. So let's suppose B sub n represents population growth due to immigration in year n. So we have our population growth of our population that's already a part of our community, and then we also add in immigration or migration. It could be negative, right? Migration away, whatever. But then our population is going to increase by the following. So y sub n plus 1 is going to be equal to the previous, which is rho y sub n. So there's our population growth of our community itself. And then when we factor in our immigration, we add a b sub n to this. So we let b sub n represent the population growth due to immigration in year n. So this b sub n is actually a sequence where all of these numbers could be different, right? They could be different. But let's see how this works then, right? So what this means, okay, so y0, this, I'm just going to leave this as y0. So it could be alpha, but let's leave it as y0 for now, just so we can try to write down a solution here. So there's our y0. Then in year 1, what is it going to be, right? When n is 1, well, according to this, it's going to be rho times y0 plus b0. Just plug in, right? And then it starts to get fun, because then in year 2, what's going to happen? Well, it's going to be rho times y1 plus b1. All right, but what's y1? This is rho times rho y naught plus b naught, and then plus b1. And then if we work this out, it's going to be rho squared y naught, y0, initial population, plus rho times b0, because now that the population that immigrated in year 1 is now reproducing with the same rate. Rho is the rest of the community, right? Plus b1. And then we can do one more before we try to notice the pattern here. But there is going to be a pattern. So y3 is going to be rho y2 plus b2. All right, well, what's going to happen? It's going to be rho times the previous. Rho squared y naught plus rho b naught plus b1 plus b2. And then we work this all out. So rho cubed y naught plus rho squared b naught plus rho b1 plus b2. And notice what's happening here. If we go to the next one, we're going to multiply rho by the initial population again, right? 1 less rho to the 1 less power times the original b naught, right? The original immigration. And then as the b's count up, the powers on the rho count down, right? And so we can write this as kind of a series solution, or at least a sum in summation form. So we obtain the following solution when there's immigration involved. We get that, all right, y sub n is equal to exactly what we had before. Remember, it was rho to the power n times the initial population. I called it alpha up here, but we've left it as y naught down here. So we could have called it alpha down here. This doesn't matter. So just so we can compare, let's actually do that, right? So let's go back and let's say, all right, this is equal to alpha. And so then at each one of these steps, this is alpha, right? This is alpha. This is alpha. Then what do we have, right? So our solution is going to be, it's the old solution, alpha times rho to the n. Rho to the nth power times alpha. So that's exactly what we had before. But then how does the immigration contribute? Well, it's going to now be the sum as k goes from 0 to n minus 1. Not quite n, but n minus 1 of, so all of this is going to be written in sigma notation. Well, it's going to be rho to the power n minus 1 minus k. So these are going to count down. So rho to the n minus 1 minus k. So that's the largest it can be, and then minus k, they're going to count down, times b sub k. So when k is 0, this is n minus 1 times b 0, right, etc. When k is 1, it's going to be rho to the n minus 2 times b1, etc. And so there's our solution when immigration is involved. Now, though, let's think about a slightly simpler case in this. So this is a general solution for general immigration where the b sub k is different, right? But it's possible. So if this b sub n is equal to b, so if this is constant, we have constant immigration, right? Then the b can actually factor out. So from up here in this formula, or even from here, the b can factor out. So then the b factors out. That's the immigration itself. And what we obtain is then, so this is yet another scenario, right? We've made another hypothesis here. What we obtain is rho to the nth power times initial population alpha times, plus b times this sum, but this sum is now geometric. So this is rho to the n minus 1 minus k. And if you just switch everything around, then actually this is the same as rho to the nth power times alpha plus b times sum. K goes from 0 to n minus 1. And we can write this then in the following way. So if rho is not equal to 1, then this is the sum. This is actually the partial sum, right? Of, and by this I just mean this portion, of a geometric series. And we can write our solution as follows now. So y sub n is equal to rho to the nth power times alpha plus b times the ratio of 1 minus rho to the n over 1 minus rho. Okay? And so this whole term right here then is the coefficient on the b term for the nth time. So when time equals n, right, the nth population value in this discrete model. All right, let's do some particular examples now. Now that we've worked out all these details and struggled through, let's see. So this one, again, this is the closed form formula for this one's for constant immigration. So if the immigration is just a constant, right? Constant immigration, that's B, right? The B is the constant immigration. This one is for variable immigration. But still, all of these that we worked out in this portion, all of these are for constant growth rate though, right? So this one right here was our constant growth rate. Okay, so those are the three formulas. Now here is an example. So here's an example. Find a solution. So solve this first order difference equation given by the following. So y0 equals alpha. So alpha here is initial population. I'm not giving you a value for it, but initial population. And then the formula here for the difference equation is y sub n plus 1 is equal to 0.5 y sub n plus 6. All right, so find the closed form solution of this. So that's our job. Find a formula for y sub n. All right, I'll give you a minute to work on that, and I'll check back in with you when you're done. All right, so this equation here actually fits into the formula for the previous example that we did, right? So this is for the population growth with a constant immigration. So this is the formula right here, where b sub n is just b. So this is constant immigration, and we can write down our formula then, right? Just by using this formula right here. So constant immigration. In this case, b is equal to 6 and rho is equal to a half, or 0.5. And then we just write it down, right? So our y sub n is going to be equal to rho to the power n. So I'm going to write 0.5 as a half. So 1/2 to the power n times alpha plus our b is equal to 6, right? And then the rest of this is going to be 1 minus a half to the power n over 1 minus a half. And then we can do some simplifying, but otherwise this is the answer, right? So this is going to be alpha, initial population, over 2 to the power n. Notice this growth rate is actually less than 1, right? So this population's decreasing in size in this sense, but there's immigration happening, right? So it's going to be this, and then when we add this all together, we multiply through by 2 to the power n on the top. This on the bottom is just equal to a half, right? So let's work it out here. So this, we'll do it in 2 steps. But this is 6. This is going to be 2 to the power n minus 1 over 2 to the power n, all over 2 minus 1, right? This is just a half on the bottom. And so when we work this out, we get this half I'm going to combine with this. So divide by a half means multiply by 2. So this is going to become 12. And then we can combine this all to be over the same denominator, right? So our solution is going to be y sub n equals alpha plus 12 times 2 to the n minus 1 all over 2 to the nth power. And so there's our population at time n, right? Remember, and this works for n equal to 0, 1, 2, etc. Counting up like that, right? So that's how this works. And there is an example for us. Let's do one more example. But it's as easy as that, right? Once we've worked out the formulas, if our example or our problem fits into a given formula, then we just use that formula, we plug in, we simplify, and then we're done. So that's all it is. It's honestly doesn't even feel like we're doing calculus, right? All right, so here's the last thing that I want to do for this lecture. This one is called the logistic difference equation, and this is very similar to our logistic growth population models, right? So logistic difference equation has the following form. For example, all right, this one is y sub n plus 1 equals rho times y sub n. So this is our population growth with our fixed constant population growth rate of rho. But then to make this a logistic model, remember what we do. We multiply by some kind of factor that looks like 1 minus y sub n. So in general, we'll just call this one 1 minus y sub n. You can change this a little bit, but this one we're going to leave just like this. So this is the first order logistic difference equation. All right, so this is a logistic difference equation. And what I would like us to do for this one, so this is going to be another one I'm going to let you guys work out real quickly here, but I want you guys to show that the equilibrium solution, or is at least an equilibrium solution, is given by the following. So y sub n equal to rho minus 1 over rho. Show that this is an equilibrium solution. All right, remember, equilibrium solution means that when you plug this in to here, you should get that yn plus 1 is equal to the same thing, right? Equilibrium means not changing, not changing. So take a moment, plug in this formula, make sure you get the same thing, and then check back and we'll finish this lecture off together. Hopefully you guys took a moment to actually check this on your own, but let's work it out together now. To show that this is an equilibrium solution, I said this before the break there, but what we need to do is just plug this into the previous one, right? So we need to compute y sub n plus 1. So this is going to be then rho times y sub n. Y sub n is rho minus 1 divided by rho, right? And then multiply by 1 minus rho minus 1 times rho, or divided by rho, there, right? So, and then we just work this out carefully. So those cancel. This becomes rho over rho, right? And then we just very carefully work out the details here. We're left with a rho minus 1 outside here. When we subtract this, I'll do it in steps here, but this is rho minus, parentheses, rho minus 1 all over rho. And then, of course, very carefully here, we have minus. It's kind of distributes, right? And then rho minus rho are going to cancel. And so, of course, this is going to be rho minus 1 times 1 over rho. Well, that's rho minus 1 over rho. That's y sub n. And so at this point, we've shown that y sub n plus 1 is equal to y sub n. So therefore, that is this right here, rho minus 1 over rho, is the equilibrium solution for the logistic difference equation. It's an equilibrium solution for this particular logistic difference equation. All right, so that's all we've got for this lecture. We'll leave it here. These difference equations, we're not going to do too much with these moving forward, but we want to make sure we introduce them because, again, as we mentioned at the very outset of this lecture, sometimes when you build a model where you're trying to model a physical phenomena, it is actually easier and sometimes even better to use discrete data rather than trying to fit continuous data. So this is just an example of how we could use discrete data to kind of model a physical situation, even though we've been using, continuous, smooth, differential equation type data and models everything else so far this semester. So I'll leave this here, and I'll talk to you guys in the next lecture.